Hello everyone, welcome to the next episode in our VESTA journey. Today I will show you how you make figures like such, where we here have a MFI, or commonly known as a ZSM5 material. You can see channels. I will also show you how to make these nice cages. You can see you can make them in different variations, but you can also look into building blocks. Here there's even two frameworks in one plot. And you can see these are all just variations actually on the chabazite structure, where you can see that all we did is change the appearance. This is the easy part, changing the appearance. Getting there is a bit more difficult, but I will show you today. So the first thing I would like to recreate is the LTA cage. Now I've opened up the ZIF file which I've downloaded from the International Zeolites Association, so you can find this online, these ZIF files, and you get the following. So all I didn't change anything, I just loaded in. And the first thing I wanted to do is to remove the complexity. For that, we can go to the bonds. Again, if you're struggling to find it, it's over here. Where it is, sorry, it's over here. Control B, I will use the shortcut, and you can find the bonds. First thing you can do is, for example, to avoid it, do not search outside of the boundary, like so. And you get already less atoms in there. You can see that to get a cage, we're almost there. This is already quite similar to what we would expect, the cage here. The only difference here is we're using only T atoms, so we're not showcasing the oxygens here in the red. That's the only thing we really have to change. So what we'll do is we'll change the bond, rather from silicon to oxygen, just silicon, and change the bond lengths. I know from experience it's about 4, and you already get quite close to what we want. Let's go to objects and remove the oxygens, and there you go. We have already our cage. Now the only thing that's really different is this is style. If you go to properties, you can play around with them for sure. Let's do a basic one. Let's make it black. Let's make the icons also black. Again, I'm going a bit fast in here, but really you can go through all these sections and play around with the settings, and then this way you can change how it looks. So if we now get our structure, it's not completely the same. I think here I only used black. Sorry. But it's similar. I mean, you have the cage. This is what you want. You can play around with the tools. Um, and you can get like a nice angle for your picture, and you're already there. If you want multiple cages next to each other, all we have to do is go to boundary and change the boundary. So let's say I want 2 cages next to each other or on top of each other like this. So, but you can also add more in every direction you want. So these all will be 8 cages next to each other, and you get nice cages. We don't see any polyhedrals. That's for another video. But this is already a nice structure. So you can see for the LTR framework, this is actually very easy. Once you know a bit how VESTA works, you can quite easily get these nice cages. Unfortunately, for not every framework type, this is as easy as such. We define these cages or these cavities really as a sort of block, while from a crystallographical point of view, this is not per se the cage. Let's take a look to the chabazite structure, and also a very common structure. Here I also loaded in the chabazite, but what you will see over here is actually that it's part of 2 cages that's loading. This is because the unit cell is not just one cage. I can show you this. This is exactly one unit cell. So it includes different parts of our of different cages, and we want to highlight one cage. For example, like such. Here, if we would put unit cells on, you would see I've taken part actually of next door's unit cells. It's not fitting exactly one unit cell in there. So we'll have to play around a bit with our boundaries as well. I will, maybe let's turn this on. Why not? What we can do is very easily just increase our boundaries. Let's say we take more space. If you get sufficient large volume, you will get, of course, some cages. Now it's a bit hectic. This is because there's a lot of oxygen atoms in there as well. I promise you there are some cages. You can see it if you go to the right orientation. But to simplify it already, the first thing I want to do is I want to hide these non-binding non-binding atoms. For this, you go to properties, atoms, non-binding, and you can turn them off. And there you go. You don't see the non-binding ones. The next step I will do is the same as with LTI. I'll go to bonds and I will change the bonds. I don't want it to search outside of the boundaries. You can see that it goes away already. And I only want it to be connected to the solution. Again, if I would do this, nothing would happen because the max lengths need to be a bit higher. It's about 4 angstrom. And there we go. You get already only the blues are connected. Now let's get rid of our oxygen atoms. So we go to atoms, we turn this off, and there we go. This is already a bit clearer, hopefully. And what you can see, if you know what you're looking for, I'll go to free rotation. We can find already some of the cages. You can envision them. Over here, for example, there's one. But you can see it goes through multiple unit cells. I'll maybe turn this off. This way it's even more clear. Over here, there is like a cage. If you don't see it, don't worry. This is how it should look like. You see, this is how it should look like, and it's hidden in there, but it's cluttered with half cages with structural building blocks. So you don't really get this nice cage just by playing around with the boundaries. A very quick and dirty way of doing or fixing this is if we would just delete the parts we don't need. So this is what I'll do here. You go to, I put it in this orientation, but you have to play around with which framework you're working with. Then you go to select, and I know here on the top there is one complete cage. So everything on the bottom I could just simply delete. We can do this like such, start really deleting it. And now you can see this looks already quite like the cage that we're going for. Here you can see it as well. Maybe if I put it in the A orientation, let me center this a bit. You can see this is the cage we're looking for. It's quite similar already. But note, I've selected it, but are still, you can see it's in 3D, of course. There are still some parts we have to delete. Again, let's just turn it sideways. You can, again, put selection on and start deleting it. And like I said, this is a quick and dirty way of doing it. And I'll show you why this is the dirty way and not my preferential way of working. We get the cage quite fast. Again, we can change how it looks. Let's do the same adjustments that we did previously. Let's put this black. Let's put the shininess at 0. And there you go. We can move it around a bit like so. You can see we have the cage. And if we compare it to the LTA, for example, it's very similar. So this would be already nice for our paper, or if you want to use this figure somewhere. If you want to scale it, you can always scale it by going to overall appearances. Let's put like 40 angstroms or something. Let me put this a bit in the middle, like this. Here we can do the same. Let's 40 angstroms. Let's choose an orientation. Maybe turn it around our y-axis like so. You get some nice angles. You can see it's a 3D figure. And if you now compare these two, you can already see like, okay, this is how they look. You can see the chabazite is actually a bit smaller in volume than the LTA. And you already have a figure. You can save these figures. You can save it as a VESTA file. You can export it as an image. And this is quite nice. But like I said, this is the quick and dirty way. Why? Let's say, okay, I have this structure, but I actually want the oxygens to show as well, because I really want to highlight there's also oxygen there. It's not really these kind of ones. You could say, okay, let's turn on oxygens again. You will get all the oxygens that were included in our initial boundary. This means you have to re-delete them all. We would also have to readjust our bonds. So it's something like, it's about 2 angstroms. But you see, if you do this, everything in the boundary gets reset. So all our work is gone. You can luckily undo this all by doing undo or Control Z, and we go back to this. But you can't really make the change without going through the work again of deleting everything. So this can be quite cumbersome. And there's a better way to do this, but it's obviously more time consuming because it's not a quick and dirty way. What we can do, I've loaded in here another zip file just to showcase that we can do this as well in a different way. And we're gonna do the same steps initially. So I want to remove all the oxygen atoms. I want to have, sorry, I do not want him to show AKs any non-binding atoms, and I want to change the bonds. So we'll change the bonds to only silicium connected, like so. And then we get the building blocks. But again, we don't have a whole cage. So what you could do again is increase this length, and then you get a full cage somewhere. You could also make use here of better boundaries. If you already think about how the boundaries look, I've done this prior by looking into the crystallographical structure. Then you can already guess like, okay, this way is going to be looking quite nice. For example, I'll showcase here like so. You get already the cage. So I adjusted already a bit of the boundaries, but what I did is by trial and error, or you look into the crystallographical structure, you can see over here that like the z-axis it's way too high. In the z-axis, which is here C, we want to be removing it from here and at the bottom as well. So that means let's remove it like so. And we get already quite close to what we want. But unfortunately, you will see there's still parts over here and over here that you want to remove to really get to this gauge. If you compare this to this, you can see we still have to remove some clutter or some parts. You could do again by selection tool, but again, you will face the same issue. If you ever have to change something, you will have to select, deselect, or re-delete again this part. So let's try to avoid it. And what we can do is further play around with the borders, but sometimes your crystallographical structure will not allow it. As such is the case here. In the chabazite structure, you will have, sorry, so the symmetry. Here we go. The symmetry, you see it's trigonal, and we have a hexagonal axis. So it's with x, y, z coordinates, it will be difficult, if not impossible, to remove them. Luckily, there's an additional tool that we can use, and it's our cutoff planes, and these do follow our symmetry. So they can remove, we can define a plane where it gets removed. The unfortunate thing about this thing is, and I'll put it on the right because you see in a sec why, is if we use this, you don't really see where the plane is placed. You have to know it based on your knowledge. Now, sometimes you can do this if you have a lot of knowledge about the crystallographical unit. You can play around with this. It's perfectly fine. But I guess most of you also maybe want to do it by trial and error, see how those work. So what you can do is, I already opened it here, but I'll explain maybe again. If you go to edit, you can add the lattice planes. And what do these lattice planes do? Let's create one. It showcases a plane in space. So this can be nice for visualization purposes as well, but today we will just use it as a sort of tool to guess where we should put a plane so we can delete the atoms that we don't want. So for example, if I would put it like so, and I will turn it a bit around, you can see, okay, this, if we play around a bit, this is already a nice orientation, but it's a bit too far from the origin. We can change this origin value as well. Let's put it like 10 angstrom. And you can see this will already cut off part of what we don't need. And that's actually quite nice. So this is a visual way of finding this. So the values you find here, you have to put them in here as well. So we'll create a new cutoff plane. We'll copy the Miller indices that we found, and this is from the origin, so it's the answer. And then we can apply it. If we now apply it, it will cut off everything that's left here of it. And this way you can remove all the atoms. So we can create a new cutoff plane. We'll look through this tool where we should place it, what the indices should be, and then do it again. So I'll show it one more time. For example, here now I'll change it like so. And I know, okay, this cuts it off as well. So this looks pretty nice as well. And we can add it as well. So we'll go over here. I'll copy the indices from here. So I've created a new cutoff plane. It's -1. I applied, and boom, there it is removed. Now, obviously, I do know them, or I prepared this already, so I know them by heart. Uh, how you can remove them. So this you may need some more time to do this your first time, but this is just for tutorial purposes. I already figured out which one I have to use. So quickly, I'll show you which one I will add as well. I know from that this one you need to remove as well. So add a new curve plane, apply it, and there we go. And then we still have just one bond over here that we need to remove. And I know it's at this position. You see, this way it will cut off the ones we don't want without touching the others. So simply put it in there. And if you apply it, so I will press OK on the cutoff points. I don't add the plane. I don't want it actually in my visualization. Let's get it back. You get the same structure as we created before. Again, if you would, let's quickly compare it, make them black, remove the shininess, like so, and we also need to change our color of our bonds like this. And okay, it's not in the same scale. Don't worry, we can fix that again. You can go to overall appearance. Is it 40? Let's keep it at 40. It's fine for me. And here, let's put it also at 40. Overall appearances. Yes, and there you go. Okay, you see it's a bit more to the top. Don't worry, I gotcha. You see, we get created 2 times the same figure using 2 methods. One is the quick and dirty methods. The other is the more robust version. And why is this robust? I'll show you. If we add the oxygen atoms again, boom, they are there, but it's only in the boundary that we want them to be. And for the bonds as well, if you would now be like, okay, I want to change it back, I want to really showcase how they are bonded to the oxygen as well. You get these bonds, and it's really nice like this. You can see there's no problem. You see the cutoff plane we could maybe put it even a bit higher, but yeah, that's up to you if you want to also get rid of these oxygens outside of the cage, but you get the idea. If we would do the same here again, this would happen. Everything in our boundary resets again. So this is quite cumbersome. If you have made this figure, but you have to change something, it's quite hard to do. Here, it's really easy. You can just remove it again and make it back to the original figure without really doing brainless work. And this is how you do it for a nice cage. Okay. Lastly, I promised to show you also how I made these figures. You can see over here, this is the same figure. The only thing I'm changing here is really the color and how everything looks. So these are the same files really, but we are changing, yeah, how it looks. For that, you have to go into properties, change it, play a bit around with the atoms, with the bond color and size, and so forth. Similar here, case as well here. This is also, I created 2 faces, put them next to each other, and I didn't even look into the appearance. I just made them in a nice orientation like this. Last thing maybe I want to show is cases like how would you make this citizen 5 figure like such. Again, once you have the tools, once you understand how this works, this goes very fast. What I did here over here is I did the quick and dirty technique for clarity, and I connected all the T atoms. So I will do this over here as well. Let's remove all these oxygen atoms, change the bonds to silicium, get it to about 4 angstroms. Okay, it may not appear like we're close, but we're actually quite close already. Change my boundaries. I think it's 2 that we used, something like this. And now you just look for the right orientation that you want. So this is the orientation that we want. All we have to do is turn it, I think 90 degrees, something like this. And you can see it's already getting there. If you have a bit of imagination, you can already see it. Only thing I think I did is I turned off the atoms here. I made the bonds black. So I made the bonds black, like so. It's not properly scaled, but it's close. I can see over here that these figures are already quite close. The only thing that's missing here is I removed some parts in the final product. So you can do the quick and dirty technique here as well. We can remove what we don't want. Let's see what we removed, like so. So I'm just selecting and pressing delete every second to remove the unwanted parts. See, it's over here. I also removed some parts. There you go. We have a very similar figure. Now, yeah, you can see from the axis that it's a different orientation. In a 2D picture, obviously, this will not show, but it's not exactly the same. But for a 2D picture, it's fine. You can see here on the side there are some parts we didn't read. You can delete them as well. But yeah, so let's make it exactly the same. There you go. This is the same picture, and again, you can quite easily easily and fast really make very nice figures. Most of the time you spend really is on changing how they look. So with that, I hopefully introduced you to what you have to do if you have a structure that is not that easy, where the unit cell does not fit exactly the building block you want, or if you want multiple facets of the structure, you can play around with this as well. You can create it's using the quick and dirty technique where we'll just create a large boundary. So that's all we did. We create a large boundary so we have enough of our structure visible, and then we start deleting until we are happy with it. That's the quick and dirty method. What we also can do is adjust our boundaries properly to begin with, and then create cutoff planes to remove any things that we don't want. It can result in the same thing, but this is more robust, so I would recommend this one. And with that, we're finishing our second tutorial. In next tutorial, I will show you how polyhedral structures work. So yeah, keep a lookout for that.